Okay, so the first subunit I want to talk about is called alkanes. Now, alkanes are simply carbons and hydrogen single bonds only. Now, when you signed up for this course, you signed up for organic and biochemistry. Basically, organic chemistry is, if you look up the definition, it'll start talking about the study of carbon, but it's also the study of oxygen, nitrogen, sulfur, and phosphorus. Those are all considered organic compounds and inorganic compounds. Now, this is totally untrue. They have a new estimate as far as the number of organic compounds, 10 to the 60th. That's 60 zeros, which is a gigantic number of different organic compounds. And those include polymers, those include biochemical molecules, just a whole bunch. Now, the big difference between organic and inorganic would be 305 compounds you studied, the different kinds of strong acids, the different kinds of salts, like sodium chloride versus calcium hydroxide, that kind of stuff. The organic compounds are kind of the opposite. Inorganic compounds tend to be ionic. That means they dissolve well in water. Organic compounds tend to be covalent bonds, meaning that covalent bonds share electrons as opposed to transferring electrons like in the ionic molecules. Forces between the molecules tend to be weak. That means they have very low boiling points as opposed to inorganic compounds. For example, methane gas is it boils like at minus 60 degrees Celsius. Sodium chloride boils at 2800 degrees. Very different.
Professor, where is this tab at? I'm looking for it and I can't find it.
Canvas, files.
Yes.
Unit
Yes.
1.
Yes.
Unit 1, and then you'll see slides.
Yes.
And look at the one called alkanes.
Chapter 12, alkanes. Thank you, Professor.
Okay, also organic compounds are non-conductors, where inorganics are conductors. It's this rate of chemical reaction. It's usually slow. There's a lot of exceptions, though. One exception would be dynamite or C5 explosive. Those are all organic, but they go really fast. Carbon has got 4 singleton valence electrons. And because of that, it can bond in a whole bunch of different ways. That's where you can get these. One molecule can be over 1 million carbon atoms long. It's just so uh, adaptable to different bonding configurations. It's amazing. Silicone, oops, is right underneath carbon on the periodic table, so its valence electrons are going to be exactly the same. So silicon can also bond in as many different ways as carbon. If you remember from 305 in the periodic table, the way it's organized is columns called groups have similar chemistry, and that's because their valence electrons are set up exactly the same way. Hence, their chemistry is the same. Now, we're going to run into this concept called isomers a lot in this class. And there's different kinds of isomers. But basically, an isomer, and this is important, isomers basically are compounds that have identical molecular formulas. Like the C2H6O. Okay, in your dry lab 0, that's one of the compounds that you need to do a Lewis dot structure for. And I did it in lecture on Monday. So basically it can be either a alcohol or an ether. Same formula. So those would be isomers of one another. And the line drawings would look like this. So we've got a carbon here, carbon there, carbon here, carbon there. Remember, line structures whenever there's an at the end, at the beginning, and if there's a kink, that's where carbon's located. No hydrogens are given, but you need to know that carbon has 4 bonds. So for example, here, this carbon here, it's got 1 bond, and then we need 3 more to complete that 4. So that's where the hydrogens would be located. This carbon here, we've got 1 bond to the other carbon, 1 bond to the oxygen. So there'd be 2 hydrogens here. And the reason why organic chemists and biochemists do it is that the hydrogens are so ubiquitous everywhere that they understand that hydrogen is 1 bond, carbon's got 4, so they leave out all the little details. Now, there's something called functional groups. A functional group is what differentiates one class of organic molecules from another. Normally, they list alcohol, aldehydes. These are all going to be separate chapters. One they frequently don't list is alkanes. That's because alkanes don't have anything but carbons and hydrogens. So the functional group for an alkane is simply a hydrogen. So it really limits its types of reactions. Okay. Now functional groups can have all kinds of stuff as part of it. You can have nitrogen. You can have oxygen. You can have phosphorus. You can have sulfur. You can have halogens like chlorine. All that stuff is considered a functional group and covered under an additional chapter. Now, these are the 3 types of structural formulas. And we are not going to use these. We're going to use line drawings because every textbook except this PowerPoint uses line drawings, including the optional textbook for this class. Or you can go to a OER free textbook. public domain textbook. If you go onto any of the tutoring sites on YouTube, they all use line drawings. Biochemists only use line drawings. Now, when we talk about hydrocarbons, they only contain carbon, hydrogen, single bonds. If that is so, it's called a saturated hydrocarbon or an alkane. Now you hear the saturation bit a lot when they talk about fats. This is a saturated fat. This is an unsaturated fat. This is a polyunsaturated fat or oil. And what they're talking about is whether it contains double bonds, triple bonds, or ring systems. The simplest one are called alkanes. Now this is under the umbrella of hydrocarbons. The simplest ones are called alkanes, and they only have single bonds and only carbon and hydrogen. And that's what this chapter is all about. So if it contains any double bonds at all, it's considered an alkene. If it contains any triple bonds, it's considered an alkyne. And we're not studying alkynes in this class because there are none of those in your body. And since this is a allied health class, we're only going to talk about stuff that is biologically important. And aromatics are specialized ring structures that alternate between single and double bonds. And these would then, these would be all considered unsaturated because they have something other than single bonds. But they usually also contain single bonds as well. So it's single plus double, single plus triple, and possibly double. And this is the special alternating single, double, single, double, single, double are the aromatics. And this is also, this alternating between single and double bonds is a particularly stable structure. That's why you see them a lot in nature. I mean, a lot. Okay. There's a formula for, actually, there are two formulas for alkanes. One is this one here. That one there. And then there's another one that's in a ring configuration. And that's that without the +2. So for example, if you have, if N is equal to 3 carbons, it would be, using this one now, it would be C3, 2 times 3 is 6 plus 2 is 8. Or it's ring, so this is ring. Now they can be straight or rings as long as it's only carbon, hydrogen, single bonded. It's considered an alkane. Now, we're going to get into this quite a bit on this idea of branching. You can have a straight chain, meaning that they're just in a linear fashion like this. And this is considered branched. Okay, this over here. So the main branch, or the main backbone is that with a branch here, a branch there. This is the main backbone with no carbons branching off. Frequently, they're referred to when you're naming them as that. And then this has got we'll get into this in a minute here, but they'll abbreviate the normal part. And this is based on a 3-carbon backbone with 2 branches, one carbon branches at the middle carbon. So, for example, here, 1, 2, 3, 4 carbons. We're going to learn this series of, if it's 1, it's meth. If it's 2, it's eth. If it's 3, it's propyl. If it's 4, it's butyl. There's a series of those up to 10. Now, carbon-carbon single bonds are free to rotate. There's an exception, though. That's if it's in a ring structure. It is not free to rotate. Okay? No free rotation in ring alkanes. If it's a linear or branched, that CC bond is free to rotate. Now, what it's going to do, it's going to rotate to be the most stable version. So this version on the left got a single carbon methyl group up there that's close to one another. Here, the methane groups are almost as far apart. If we redrew this, so the H is there, and the CH3 is down here, that would be the most stable version of the free rotation. And this is called steric hindrance. So the one on the left has the most steric hindrance, the one on the left on the right has the least steric hindrance. Now we're going to find that is, there's a saying I say in this class throughout the whole semester. I even say it in my inorganic classes, is things go to the most stable point from the least stable point in the universe. So if this is least stable, that means it's going to want to go to here by that rotation on the carbon-carbon bond. Now, there's a term here called conformation. That is a fancy word for just what is it, what shape is it in? What conformation is it in? So we have 2 here. Which do you think is more stable, right or left?
The right side?
Why?
Because it's, oh, better lack of a term, it's fanned out more. It has more
Symmetry.
room to split.
What happens here is this here bond can rotate. And this one can rotate. What's going on the right one is that you've got some steric hindrance going on between these 2 methyl groups, these 2 1-carbon groups. Now, the reason why groups don't like to be around another group is because they have electrons, and electrons repel each other. So you want to maximize the distance between parts of the molecule. the left one does that by turning this one downward. By twisting. And this one goes up. That maximizes those distance between those two groups. Where this one, it's minimize the distance. So the left one is most stable. The right one is least stable. And it has to do with these groups wanting to be apart because those electrons are repelling each other.
Understood. Thank you.
That
Wait,
makes sense?
so the because of the repulsion force, it's making it less stable?
Well, it drives, the repulsion force is what drives one to become more stable than the other.
Okay.
The repulsion, see, every one of these can rotate. Okay, this one here rotating is not going to do anything. This one here rotates, though, is going to move this up and down. So this is the same deal as over here. So what happens is, as they rotate, they're going to become more stable or less stable. So it's going to rotate till it becomes the most stable, and then kind of stop there. Not totally stop, but kind of stop. So it's going to want to hang around the most stable version.
Okay.
Okay, now this is something that gives students a lot of trouble in the beginning. Is these all have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, they all have 5 carbons. But some of them are the same, some of them are different. Now, how do you tell them which is different, which is the same? Okay, you're going to be doing what I'm going to do right now zillions of times throughout the quarter. I used to work on a quarter system on the semester system. There's something called a backbone. Okay, and the backbone is the longest chain of unbranched carbons. Now, when I say branched, that means where we have carbons coming off of a main backbone. Here, there are no carbons coming off the backbone. Okay, so let's go back here. All right, so let's look at this. We have 1, 2, 3, 4, 5 carbons in a row. No branching. Now, what I usually do is I take a highlighter and highlight the backbone. And then I ask myself, are there any carbons not on the highlighted one? For example, this one has a carbon not on the backbone. Now, we could have also gone like that as well. Okay, both those are legitimate backbones. Because remember now, these single bonds can twist. Okay, let's do it again here. Let's do, come back to yellow. Okay, that has no branching. There are no carbons off that. Here. Now the key word here is longest. So this here, it's got 4 carbons long. If we did this, it would only be 3 carbons long. We could also do that. That would be 4 carbons long. So now we have 2 backbones that contain 4 carbons. Both of them are legal. The one that's not legal is the first pink one I did. That only has 3. Now, why this is important is this determines the naming of the alkane. There are 3 parts to naming organic compounds. One, you name the branches, one, you name the backbone, and the other, you name the functional group. Every single organic compound is named using those 3 parts. Now, the one part that's optional is if it has no branches, and it only has 2 parts. Now, we're going to get into naming a lot in a minute here. Okay, does everyone okay with this longest chain bit? The toughest part in this chapter is going to be naming, because it's going to be tricky because you have to figure out the longest chain. Okay, so these are both 5 carbon alkanes, no branches, no branches. Okay. So I would recommend highly that you use a highlighter for the rest of the semester, or multiple highlighters. Okay. Both these molecules have branches because we have molecules that are off the main backbone. Now, one way to tell whether a molecule, a carbon, is off the backbone is if you have to lift your highlighter off the paper to include it. Up here, I was able to keep the highlighter on it the whole time. Here, I'd have to backtrack or take my highlighter off and come up and hit the carbon up there. Same thing here. Remember on this one, there were 2 4 carbon. That's a 4 carbon as well. So in this case, with the pink, the branch would be here. With the yellow, the branch would be here. Okay. An alkyl group basically is an alkane stuck on another alkane. And it's missing a hydrogen because it needs to bond to that original alkane. Okay, so these are typically branches, and this is where the name of the branch comes from. Now, you need to know these. So A branch cannot have more carbons than the backbone. So let me show you what I mean by that. Okay, so here in this one here, we have a 1, 2, 3, 4 carbon main backbone and a 1 carbon branch. So the branch for this 4 carbon backbone cannot be more than 3 carbons long. So branches always are smaller than the backbone. No exceptions. Notice a 1 carbon branch is called methyl. 2 carbon branch, ethyl. 3 carbon branch, propyl. 3 carbon branch, isopropyl. The difference between these two is where the bonding occurs to the main backbone. Here the bonding occurs in the middle carbon. Here the bonding occurs on the end carbon. So if we have a 4 carbon branch, going to be called butyl, attaches on the end. If it attaches with the second carbon in, it's called sec-butyl. If it attaches on the end, second one in, it's called isobutyl. If it attaches in the middle carbon, it's called T-butyl, which is short for tertiary butyl. Now, in this class, I'm not having you memorize the butyls, but I am having you responsible for these guys. So, super important. And you can also have other branches. Now, we're not going to do these till we get to that chapter. But, and there's no fluorine in our bodies unless we treat our teeth with fluoride. So the main one actually, and not iodine either, the main one are these two here. So those can also be a branch. For example, if we had, that's a 3 carbon backbone with a branch, chlorine branch at carbon number 2. Okay, so I mentioned there are 3, now we're getting into naming now. There are 3 parts to a name. The first one is optional because if there's no branching, we can leave that one off. However, these 2 are required. So you're going to need to know these guys called flashcards when you're doing this. And the weird ones, these are 2 weird ones. You've probably never heard of hepta or nona. Okay. Number 1, identify the longest chain. So let's do that. Well, there's a couple ways to go. We can go like this. We can go like this. We can go like that. So which is the longest name? Longest backbone?
The pink one?
There are two longest ones, pink and yellow. The red
Pink
one's
and
only 3 carbons long. So let's get rid of it. Okay, so we got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So there are two of them, yellow and pink. Okay, the slide decided to choose the yellow one, but you could choose either one. Let's get rid of the pink one now, simplify things. Okay, now there's also numbering. The backbone carbons are to be numbered. And the reason why you need to number them is because we need to identify what carbon the branching is on. Okay, now they refer to that as attached alkyl groups. Okay, so here is the branch, and we can number the backbone 2 ways, from left to right, right to left. So the way we're going to name this now is 3 parts. If we're talking about alkanes, that's the functional group for alkanes. That's going to be called A and E. 5 carbons long, right? That's called a penta. Okay, but we have a branch. The problem is there are 2 ways to number this. We can number it starting here. Going from left to right or right to left. The correct one is the one that gives the branch as the lowest number. So is it 2-methyl or is it 4-methyl? Which is smaller, 2 or 4?
2.
2. The correct answer is 2-methyl pentane.
Sorry, I'm a bit confused. Where did you get the prefix? Like the 2-methyl?
Okay, so
Okay,
meth is 1,
gotcha,
penta is 5.
gotcha. It's an ethyl group.
Methyl's 2, propyl's 3, etc. So when we have a branch,
Okay, so branch.
with 1 carbon, it's a methyl branch. 2
Oh,
carbons.
I see. Oh, I see what you mean by. Oh, I got it. Okay, and there's 2 methyls, 2 different branches of the same
You can have multiple, we're gonna get into that, but we can have multiple branches.
Right, okay, I understand. The 2 comes from the 2 separate branches, right? Is that what you're referring to?
Only 1 branch for this. Only branch we have is the one I have circled.
But two is the position I think, right? What carbon the methyl group's attached to?
Exactly, exactly. The 2 refers to the backbone carbon number. So
Wait, that
yellow's the
just
backbone,
confuses the
but we
crap.
can number it 2 different ways.
Okay,
Right.
gotcha. Oh, we go with the lower number. That's what you mean. Okay.
And this slide only shows it one way, the correct way, but I like to show both ways.
Okay, that makes a lot of sense. Thank you. I
And then,
appreciate it.
and then you make a decision which is smaller. It's always the smaller one is more correct. Now, on a test, if you label this 4-methylpentane, and when we were 6 points, I take off 1 point. Because you really understood the structure. And the reason why I focus on structure, on naming, because then you have to really look at the structure of the molecule.
Okay, gotcha.
Now, I frequently leave a space between the branches and the backbone. For this slide, they put them together. I like to keep them separate because for you, it's cleaner. Okay, so every time I'm going to do the same thing. 1, identify the backbone. Number 2, identify the functional group. And number 3, figure out the numbering on your backbone, which will give you the lowest number for branches or attached alkyl groups. Every single time. Now, alkanes, so this would be for alkanes. And that's considered the functional group. If we're working with alcohols, it's going to be different. It's going to be an OL. If we're working with aldehydes, it's going to be something else. Ketones, acids. They all have different names for their functional group. So then when you see the name, you can create a structure from that name.
Exciting stuff.
This is why there's no math in this class. unless,
Yay.
unless you count counting on the main backbone. That's the extent of math in here. Okay, so I alluded to this. Let's do some examples before we get more complicated. So let's go over here. All right, and I'm going to use line structures instead of the C and the H's. Okay, so let's do that. Let's name that. Okay, now I'm going to name this one, and I'm going to give you some examples where you're going to try it on your own. All right, we got to find longest backbone. Okay, well, here's one, 3 carbons long. Here's one, 1, 2, 3, 4. Um, 1, 2, 3, 4. So there are 2 4-carbon backbones and 1 3-carbon backbone. So we're going to use the 4-carbon backbone. So let's simplify this. Let's get rid of, let's use the pink one. Okay, so now we have a backbone established. 4 carbons long. 4 carbons is, we go back up to this chart here.
Petra? No.
4 carbons is going to be like butane. It's where the bute comes from, and butane is 4 carbons long.
New prefix. Good.
Okay, so, and because it is a alkane, it's an ANE. Okay, it's a butane, but it's got a branch in it. What carbon number is it? Well, you can number it, always number it two ways. 1, 2, 3, 4. 1, 2, 3, 4. And it's a methyl group because one carbon. It's going to be methyl butane, but what's the carbon number that the methyl group comes off of? 2 or 3?
Two.
2. 2 smaller than 3. 2-methylbutane.
Professor, I have a question.
Sure.
How do you know it was methyl?
How do you know it's methyl?
Yeah.
If you go back up to here, 1 carbon, methyl. 2 carbons, methyl.
Oh, okay.
So there's some flashcard city coming
Yeah.
up here.
Yeah, a lot of flashcards for sure.
And these, if you do enough of them, it's very straightforward. But you've got to do your due diligence and do practice quite a few of them. And try lab number 1, you'll be practicing that. Now, dry lab 1, let me talk about it a little bit. Dry lab 1 is for next week, but Monday we have off. So Monday, folks, you're going to be doing it at home. Wednesday, folks, you can do it at home for Wednesday. And whoever wants to be in class for Wednesday, you can go to the Wednesday lab.
Gotcha.
Okay, so let's do some more here.
That's 1, 2, 2.
Okay. Let's name this guy.
3, 4, 5, 6. Mixing. And there's 2. Okay.
Okay, so let's get to this here. Okay, so let's look at here. We have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Okay, there are 2 6s. So let's do
Left to right.
yeah. Now you could also do this one here. That's 6 as well.
Yeah,
So let's do the yellow one.
sounds good.
Okay. All right, so remember we have 3 names. And we're working with an alkane, so that's ANE. Okay, 6 is hex,
Yes.
so that's going to be a hexane. All right, and we do have a branch.
Yes.
We're going to number this 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. Okay, and the branch is how many carbons long?
2.
2. So it's going to be ethyl. And is it on carbon 3 or 4?
3. Carbon 3.
3. So we have 3-ethyl hexane.
That's a lot of math.
Professor?
Yeah.
Why is it carbon 3?
Depends what you can number this from left to right and right to left. So what you do is you put both of them down and see which number is smaller for that. This is our branch right here. And it's on either on carbon 3 or carbon 4, depending on what direction you're numbering. And you want to pick the lower number.
Okay, thank you.
Does that make sense?
So if it branches three times, then it'll be propyl.
Say again.
If it branches 3 times, then instead of ethyl, it'll be propyl.
Yeah, you can have branches of propyl,
Iso.
butyl, isopropyl, any of those in that one chart I showed you.
Okay. But we don't gotta learn or we don't gotta know past isopropyl, right?
Correct.
Okay, thank you.
Professor, I had a question in relations to kind of like the whole naming structure. So the functional group gives you the ending of essentially the name of it, right?
Okay, so this is the yeah, the ending is the functional group name.
Gotcha.
If it's an alcohol, it's going to be different. If it's a double bond in there, it's going to be, instead of ANE, it's going to be ENE. If it's a triple bond, it's going to be YNE. So just that identifies what it is. And you're also going to have to identify where the functional group is located, except for alkanes. Because alkanes, the functional group is an H, which is a whole bunch of H's. So you're just going to leave it alone. But if we had an alcohol, for example, we'd have to identify what carbon on the backbone is the OH group.
Gotcha. Thank you.
And then this guy is strictly how long the backbone is. And this is branches. Now, we can have different branches, and we can have multiple branches. So those are going to come into play with terms of one, you have to name. If there's more than one, you have to name how many there are using di, tri, tetra, penta, etc. And then when you name them, when you put them down in the first part for the branches, you put them in alphabetical order. And you ignore the di, tri, sec, t, except for iso. Okay, so let's do this with a line drawing here. Okay. So that's same as a line drawing. All right. Step 1. Let's identify backbone. Okay, here's the way I drew it is going to be obvious what the backbone is. Which is going to be 6, 7 long. Yeah, so, okay. However, we have branches. We have multiple branches now. Okay, we've got some 1-carbon branches and we have some 3-carbon branches. Okay, these are going to be methyl branches. Same with that. This is going to be 3 carbons, and there's 3 carbons. There's N-propyl and isopropyl. Now, a little gimmick on knowing these is if it's got the S in iso, think of the word snake.
Okay.
What does a snake's tongue look like?
Oh, like that.
Yeah,
a fork.
exactly like that. Forked tongue. So whenever you see that forked tongue, think of isopropyl. Okay, so we have 2 methyls, isopropyl, and 7-carbon long backbone. Okay, so the functional group is an ANE for an alkane, and 7-carbon is called hepta. So heptane is the name of this main group, the main backbone. And branches. Now we've got 3 of them to deal with. We have 2 methyls and an isopropyl. Now, which comes first, I or M?
I.
I, so we've got isopropyl first. I probably unmuted myself. I really want to hear one, tell me a little closer. Okay, and then we have a dimethyl, di meaning 2. And now we have to figure out the numbering scheme here, okay? So let's keep this. Okay, so we can number from left to right, right to left. So this is 1, 2, 3, 4, 5, 6, 7. And then we can have 1, 2, 3, 4, 5, 6, 7. Okay, it looks like left to right gives us smaller numbers. So the 2 methyl groups are going to be on carbons 2 and 3. 2,3 dimethyl heptane, and the isopropyl group is going to be on carbon number 4. Okay, any questions on that?
Yes, quick question on the like which order to pick the number, right? So like why dictate the smaller number? So it's just a smaller number overall. It doesn't matter what branch. It's just like as long as like you have a smaller number, then because I'm looking at like the dimethyl, right? You could have. Oh, I guess you're going with a 2, 3 just because that's the smallest.
Whenever this die, you have to have 2 numbers associated with it. If this
Right.
is dry, you have to have 3 numbers associated with it. And you can come off the same carbon also. You could have like 3,3 dimethyl heptane. That means the 2 methyl groups coming off of carbon number 3.
Gotcha. Okay.
Okay, so let's do, um, okay. Go ahead and try this one on your own. See what you get. Okay, so let's start on this guy here. Okay, again, the way I drew it, it's kind of obvious where the main backbone is. Okay, and that has 1, 2, 3, 4, 5, 6, 7, 8 carbons. And it's an alkane, so it's going to be an octane. And notice we have two A's together there. You eliminate one of the A's, so it's octane. Now the branching. Okay, we've got a couple of methyls and another isopropyl. Okay, so we have to determine numbering. Now, since more stuff is towards the left, that's probably a good place to start numbering. Okay, so we have two methyl groups on carbon number 3 and an isopropyl group on carbon number 5.
So you do 5 isopropyl, 3 methyl.
How many methyl groups are there?
Di.
Right.
Methyl.
Okay, and the methyl groups on carbon number 3.
It's like a stupid question.
I'm sorry, what? So 5 isopropyl 3,3 dimethyl octane. How's that for a mouthful?
That's cool.
I think that was background noise, Professor.
Professor.
Yeah,
For the isopropyl, couldn't we go from the right side and it'd be 4?
okay. All right, if we number it from the right side. Okay, so we're gonna have 4 isopropyl, 6, 6,
Oh, so we have to go one way for both.
yes.
Okay, that makes sense. Thank you.
Yeah, so, and just look at the numbers, which group is smaller? You know, the top one's,
Yeah,
bottom one's 16, so 11 wins.
I just thought it was like what's called separate for each like naming group. So like
Right.
I was like
Yeah, in fact,
yeah.
when in the next chapter, when we get out of alkanes, actually the one that determines the numbering is the functional group, not the branching. The only one that is determined by the branching is alkanes. Every other functional group is determined by the functional group. Like we were on alcohols, which carbon is the alcohol off of? You know, and whatever number is lowest, then that cements the numbering for the backbone. And then branching is determined from that. Okay. We can also have ring structures. So, and that's denoted by cyclo.
Nothing. I was able to think of that. I thought they were like pretty good. I'm still not.
You guys want to talk some more about this guy?
No, okay.
Professor, can we do another example? Or like, just give us one and then we'll try to do it, just so we can get more idea.
Well, I want to stop for a second. And
Remember.
okay, if we go to Canvas and go over to Unit 1 worksheets under Files, I have some worksheets, additional worksheets for practice as well. For example, this guy here. Lots of practice. And we haven't talked about how do you go from a name to a structure yet. But this, and I have a series of these worksheets as well. So, and then there's, if you just do a Google search on alkane worksheets, you'll get lots more as well. So that's under Files, Unit 1,
Thank you.
Worksheets.
Oh, it's okay. Thank you.
And then there's another file where the answers are, by the way, too.
Okay, thank you, Professor.
Sure. Okay. All right, and then there are the cyclos. So everything's the same with cyclos, except one thing that's really important is I mentioned this before. Ring structures are rigid. And I want you to note here now as a flag, anything that's rigid, that's carbon-carbon single bonds are not free to rotate. Is in one configuration only.
Excuse me, you dropped something.
I'm sorry, say again?
I don't think that was for our class.
Okay, and cyclohexane is the most stable. And cyclopropane is the least.
It's just
Okay. Ring structures automatically identify backbone. So if there's a ring involved, that's the backbone. Like in this case here, we've got, it's a 5-membered ring, and we have, that'll be the backbone. And then we have an ethyl and a methyl branch. So it's a cyclopentane.
what the
Cyclopentane, and we have 2 branches, an ethyl and a methyl. So which is lower, E or M?
uh,
So the ethyl comes before the methyl, and we can number this 2 ways, clockwise and counterclockwise. So we can go clockwise is 1, 2, 3. Counterclockwise is going to be 1, 2, 3, 4. So the first one is going to give the methyl as a 3. The other way, it'll give the methyl as a 4. And we can start counting at the methyl or ethyl also. And just whatever ends up being the lowest number. So because 3 is lower than 4, we're going to go with that. So it's going to be 1 ethyl. 3 methyl. But again, on cyclic compounds, you typically want to number both ways and see which one gives you the lower numbers. And you always want to start numbering on, if it's got branches, start numbering on one of the branches. It doesn't matter which one. And then see which the numbers give you. So in this case, it could be 4 numbering sets. So we started with the methyl group. 1, 2, 3, 4, 5, 6, or 4, 5. Or if we go clockwise, 1, 2, 3, 4. So one of them's going to give you the smaller set of numbers. All right, so let's do another one here. Um, okay. Go ahead and try that on your own.
This is
Okay, so let's analyze this. Okay, so we have a ring structures that automatically means backbone. And we have a methyl group and an isopropyl group. So we'll start numbering here. If we number counterclockwise, that's going to give her lower numbers. But there's still two ways to do this. That's one way. The other way is to start. The other way is to start with the methyl group instead of the isopropyl group being number one. Okay, so this is going to be cyclohexane. And we've got a branch at 1 and 2. Iso is lower than methyl, so it's going to be 1 isopropyl, 2 methyl. Okay, that's what's starting on the carbon where the isopropyl is located. What if we start on the methyl instead? So that's going to be 2 isopropyl, 1 methyl, cyclo.
I had a question.
Okay, so these are equivalent as far as our class is concerned. Now we're using something called the IUPAC International Standard for Naming Compounds. You can take a whole class on just naming, which the purpose of this class is for you to not become experts at naming. The purpose of this class is to introduce you to organic and biochemistry. So these two namings are equivalent for testing purposes, okay? All right, so we've okay. Do you understand the difference between isopropyl and plain old propyl? Yes, exactly. Snake's tongue. Whenever you see this forked right there, think of isopropyl. Okay, if it wasn't isopropyl and just plain propyl, this is what it would look like. That's what
Like a
propyl
little
would be.
lightning bolt.
Oh, okay, yeah, I was just confused about that. Thank you.
Same number of carbons, 1, 2, 3, 1, 2, 3. It's the attachment point that's different.
Molly? Hi. Hi, how are you? I'm good. I was like, I recognize that. I know, I was like, you look familiar.
Can you mute her? Sorry. I don't want to be that guy, but
Okay, I want to do
Bajais, can you please mute your phone? Thank you.
okay, so I want to go into I'm going to not go any further here. That's going to be for next week. What I want to talk about now is going from a name to a structure.
mm,
Okay. What's the functional group? Backbone. And then branching. Now these two can be interchanged. You determine the backbone first and then the functional group, either way. Okay, so let me give you an example. Let's see. So 2,3-diethyl pentane. Actually, let's make it not pentane. Let's do heptane. Heptane. Heptane is 7 long. Okay. And let's change this also. The reason I keep changing stuff has to do with the backbone is going to change. So let's do 3,4-diethyl heptane. Okay. So first thing is, what's the functional group? ANE, so it's an alkane. That means it's just carbon and hydrogens. Backbone is hept. That means it's 7 carbons long. So we go 1, 2, 3, 4, 5, 6, 7. And branching's on carbon number 3 and 4. Now you get to determine your own numbering when you go from name to structure. So let's just throw them on the left side. Carbons 1, 2, 3, 4. So that's 3,4-diethyl heptane. So there's the backbone.
It doesn't matter where we put the branches, right? Like on top or bottom, as long as it's at 3 and 4.
Correct. Whatever looks good to you, that's fine. Everyone get his question?
yes. Whether it's like on top or bottom.
Be like that too. Doesn't matter. Or if you wanted to put them on the other end, if you started counting over here as 1 on the right, 1, 2, 3, and 4. When you're drawing your own structures from a name, you can determine your own backbone numbering. So you can go left to right, right to left. Let's go, let's see. Okay, 2,3-dimethyl cyclopentane. Cyclo is ring. Sometimes I draw it like this, just make a house. Either way is fine. Now again, you can do your own numbering any way you want here. 2,3-dimethyl means they're together. Now, a better way to name that would be 1, 2-dimethyl cyclopentane. So that way you'd start your numbering here instead of over here. So most of the time, students have less trouble going from name to the structure than going from structure to name. Over the years, I've noticed that. So those worksheets I gave you, we practice both. Now, what I want to get into next week is more isomer stuff. And you're going to come up with something called geometric isomers, cis and trans. And you've heard of trans fats, and this is related to that. Then we're going to get into physical properties. And then we're going to talk about, we're not going to talk about bonding. It's out of the scope of the class. And talk about reactions. Okay, so that's what I wanted to cover today. Getting you through the structures of non-isomeric alkanes, both name to structure, structure to name, a little bit on the physical characteristics. Okay, so I will see you all around 2:30-ish for your Wednesday, folks, and I'll have your handouts for you also. Now, if you were supposed to be on Monday's lab and you didn't make it for whatever reason, just come by on Wednesday today and pick up your packet. And I understand there are possibly 1 or 2 more packets from last spring still available at the bookstore. So I'm in the process of reordering them. So we had to change vendors because the one went out of business. So that paperwork's all been submitted. It's just a matter of turnaround time. Meanwhile, I'll always give you digital copies until you can actually buy your own. All right, any questions about anything?
Just one quick one. We only need to do like the lab report instead of the lab notebook for the wet labs, or is that also for dry labs as well?
Wet labs only.
Wet labs only. Perfect. Thank you.
For your dry labs, just fill out the
The worksheet. Got it.
and you're going to submit them the same way though. If you go to assignments. Let me get out of this. Move over to
Professor.
yeah,
For next Monday, since it's Labor Day, do we still have class?
No.
I'm not sure if you
no, the campus is closed on Monday.
are. Okay. Are we still gonna have a Zoom meeting or no?
No,
Thank you.
it's a holiday for everyone.
It's a holiday for him too.
Now, if you,
Professor,
yeah,
I'm sorry. I was just wondering about the homework breakdown. The packet isn't really numbered. So I'm just wanting to know the exact pages to submit for dry lab 0, 1, 2, 3, 4 before the 4th.
okay, the difference between 0 and 1 is you'll get into a multiple choice.
Okay, so the lab 1 is where organic compounds, alkanes, multiple choice questions begins.
Exactly. And dry lab 2 is where is multiple choice questions, alkenes, E-N-E instead of A-N-E. And then there's one dry lab multiple choice for alcohols.
Okay, thank you very much.
Okay, what was I going to show you on Canvas?
The homework? No?
Yeah, I'm clicking on worksheets here. Why isn't it working? Okay. See, this will be one for this chapter on alkanes, and we have one for alkenes. There's another alkanes as well. So it looks like there is, not counting the answer sheets, 1, 2, 3, 4, 5 worksheets for additional practice. These I like a little better than the dry lab multiple choice, because the dry labs don't have line structures. They only have the condensed structures in them. And these worksheets have line drawings instead.
Professor, I have a question. So on a test, are you going to give us the line structure or the condensed structure?
Line.
Okay, sounds good. Thank you.
Yeah, once you get used to looking at the lines, line drawings, they they're just in one biochemistry only has line drawings because the molecules tend to be very complex. In organic chemistry, they're not as complex, but they still use the line drawings. Rarely do they use the condensed, with the H's and all that stuff. Never. It's always line. So I don't know this book that our school used, from which the PowerPoints came from. They liked that book, and I was kind of forced to use their PowerPoints, and I've been using them ever since. So this is like the 19th time, no more than that. This is the 19th year I've used these PowerPoints, and I've taught it multiple times during the year. So these PowerPoints I know really well. The only thing I'd like to do is modify them so that the line drawing versions would be in there more. they're good PowerPoint. It's a nice balance between graphics and text. I've got other ones that are mostly text, which I don't like. You can read as well as I can read. And then other ones are significantly more difficult. So this is a nice compromise, except for the line drawing part. So Caitlin, did that make sense what you said?
I'll just,
I'm
I'm
looking at
coming
the
in
chat.
for Ron. I'm
Huh?
coming in for Ron today, so I'll come in and ask you as well.
Okay. All right. I guess I'm going to end this and render the video.
Professor, one more thing.
Yeah.
Yesterday I went in to Canvas to look for the pre-recorded Zoom meet we had for Monday. I couldn't find it.
Oh, okay. Let me
I was gonna ask about that too because I looked everywhere for it and it's just from like 2023.
right.
Right.
I'm trying to pull up, let's see, where is files? Okay, so zoom out of modules. Yeah, it should be right here. Okay, I know it's been rendered and everything. It looks like I forgot to upload it then. I'll upload it right now, actually. And the next
Thank you
one-
so much, Professor.
Yeah,
Thank
just
you.
keep me on track, okay?
Yes, sir.
Okay. All right, you guys, take care. I'll see you Wednesday, folks, in a little while. And then I'll get this up. I won't upload it before I go though, because I don't have enough time, but because I want to get there by 2:30. Now, if you want to come in at 2:30, grab your handout and then do Dry Lab 0 at home, that's fine. I have no problem with that. Dry Labs, you can do them while I'm there, or you can do them at home. It's a worksheet, basically. Okay, all right, everyone, take care. And if I don't see you today, have a great holiday.
Take care.
Thank you, Professor.
Sure. Bye-bye.
Bye-bye now.